So let's take a look at an example. Let's say we apply this to an ideal gas molecule, a lone molecule, all alone by itself in the universe. So and let's take the typical case where if you have a sample of an ideal gas, you'll learn that the average kinetic energy of the molecule is 3 halves kT. Okay, so that's 3 halves times K. K is Avogadro's number, Boltzmann's constant. So that's the gas constant, 8.314 joules per mole per Kelvin, divided by Avogadro's number, which is 6.02 times 10 to the 23rd per mole. Okay. And our temperature is, let's just say, 298 room temperature. So what would be our average energy of our molecule? So let's do this on MathCAD. Okay. So our kinetic energy would be E equals 3 halves times Boltzmann's constant times temperature. Okay, so we have to tell it what Boltzmann's constant is. K equals 8.314 joule per Kelvin per mole. And that's divided by Avogadro's number, 6.022 times 10 to the 23rd. Let's just call that n sub A. And Avogadro's number is n sub A equals 6.022 times 10 to the 23rd per mole. Okay, so what's the value of Boltzmann's constant? K equals, oops, it's not 0, but it's less than 10 to the negative 15, so it's showing it at 0. Let's set our format so that our zero tolerance is less than 10 to the negative 15. So let's make that 10 to the negative 300. So that's your Boltzmann's constant. 1.38 times 10 to the negative 23, and you can put that in terms of joules. That's joules per Kelvin. Okay? What's our temperature? Let's define our temperature. Notice it's not complaining about that T, because T is one of MathCAD's predefined variables, so we have to override that definition with our temperature, which is 298 Kelvin. Okay, so our energy is equal to 6.171 times 10 to the negative 21 joules. Okay, what's the mass of our helium atom? Let's say our helium atom is our ideal gas atom. Mass of helium is 4.00 grams per mole, right? Now let's express that in kilograms per atom. So divided by Avogadro's number, 6.02 times 10 to the 23rd per mole. That would get rid of gram. Gets rid of per mole, right? So that's per gram. That's grams. And how many kilograms in a mole? Actually, I don't have to do that conversion anymore because it will tell me the answer in kilograms. Okay? Or if you want, you can manually show the conversion here. You can say times 10 to the negative 10 to the third 10 to the negative third kilogram per gram. Same thing. You don't have to put that conversion factor in because MathCAD knows how to adjust your units. Okay, so that's your mass. What's our K? Square root of 2 times the mass times the energy divided by h bar. How did I figure that one? What did we say energy was? Energy is h bar k squared over 2m, right? So 2m times E, square root of 2me is equal to h bar k, right? That's your momentum. And k is just square root of 2me over h bar. So let's define h bar. It doesn't know what h bar is. So h is 6.626 times 10 to the negative 34 joule seconds. And what is h bar? H over 2 times pi. Right? 2 times pi. So what's our k? That's our k. 8.856 times 10 to the 10 per meter. Okay? So what is our psi? Psi of x equals okay, our helium atom is moving to the right. So it's just e to the 1i, that's your I, times k times x. Okay? And your momentum is how much? It's just h bar times k, right? So momentum is 9.054 times 10 to the negative 24 kilogram meters per second. What's our de Broglie wavelength? Remember the formula for de Broglie wavelength? H over P. So de Broglie wavelength is 7.3 times 10 to the negative 11.